All right, let me briefly introduce the purpose of these seminars. As I mentioned before, as a KCITY US office, actually, let me introduce myself. I am Hwanil Liu from KCITY US office. KCITY is one of funding agency from Korea under Ministry of Industry and Energy. So we are kind of funding for the Korean companies to make innovation in the industry field. So one of our goal is to introduce famous and popular, well-known, renowned scientists to Korean companies and researchers, so that we can make more R&D project with Korean companies with and researchers from the United States. So that's one of our goals is to for this webinar series. Thank you for having this series of webinars for as a series to the next one with the Yale scientist. So thank you for Dr. Kim, and we'd like to have keep going webinar series so that we can make more connectivity to Korean companies with the US scientists. So please join for the next seminar webinars. And we also have another universities, not only for the Yale. So if you are interested, please feel free to contact KCITY US office to me or the other personnel. So yeah, and after the webinars, if you have any questions or any interest to the Korea, a- anything, and you can contact us. Thank you for having this speaking webinars, Dr. Hu as well. Thank you.
Thank you so much. My name is Jae-Hong Kim. I'm the director of the KCITY, and in my background, you can see the name of our center. So, I am extremely pleased and honored to have Professor Liangbing Hu to be our first speaker. Professor Hu is a Carroll and Douglas Mellamy Professor of two departments, Electrical and Computer Engineering and Material Science. He also serves as the founding director of the Center of Material Innovation at Yale. He recently joined Yale in 2024, coming from University of Maryland with exceptional research record. He has published over 450 peer-reviewed publications. So if you spend time just reading the title of his paper, that's like 50 minutes. He has published more than 10 papers in Science and Nature, but his contribution is not only in the fundamental science. His work has been recognized by many industries, startup companies, and he has earned numerous awards in his contribution to the science and also the promotion of technology transfer. Um, I'm not going to steal too much of his time. His research spans across many fields. He's going to talk some of those in today's presentation. I can easily imagine that he can have connection to many industry partners in Korea, ranging from batteries, materials, robotics, you name it. Material is the core of advances in a lot of industrial technologies. And again, I am extremely pleased to have Professor Hu. Um, we are speaking in English, but toward the end of the presentation, I'll be happy to speak Korean. If you wanna have more discussions, I'll be happy to lead a Q&A. Again, we are going to have this recording in our KCITY website. If you missed it, it's okay. We are going to send to all the industry partners for the next couple of weeks. All right, Professor Hu, is all yours now.
Very good. Thank you so much, Jae-Hong, for having me here for this KCITY seminar opportunity. I'm a professor here at Yale in the Department of Material Science and also ECE. My core interest is about inventing new materials for emerging technologies And at the same time, I'm very interested in how to scale up the technology to make a real life impact. So my research can be divided into three major areas. The first one is about heating using renewable energy called electrified heating. As we make this shift to an electrified future, heating is one of the key components. More than 50% of the energy is used for heating. So now we have a new way of heating and to make new materials. And I'm going to give you a few examples about how we can come out with new heating protocols that allows us to make new materials that is not potentially energy efficient, but also I think more important, can make much better materials. The second research category in my group is really about energy storage with a focus on solid state batteries. We are interested in new solid state electrolyte, like new membranes made of ceramics, new membranes made of cellulose fibers, how to make ion conductor materials that can basically enable new battery technologies. So the third research direction is about engineered wood, especially through nanoscale engineering, and how can we making wood even better to come up with new structural materials, for example, as a lightweight material. So today I'm going to give you six quick examples, and each one I'm going to talk about what is the motivation, what is our approach, and what kind of impact we can make if successful. So the first example about Superwood, and we want to basically engineer wood to revolutionize the timber industry, right, through the nanoscale engineering and benefit from all this nanotechnology development over the past 30 years, right? So here we're dealing with the most abundant materials, right? On average, we have about 400 trees per person worldwide, right? So there are about 3 trillion trees, right? So indeed, this is one of the most abundant material. I think everybody's actually love trees, and and people actually have a harmony actually when you live around wood, then much more harmony than living with a lot of steel and concrete. But this material is actually a nanomaterial at the same time. If you zoom in now with the current technologies, you can really understand what's going on in the piece of wood. And if you look into the details, one of the key component among all the biomass, including wood, including bamboo, including grass, you have this amazing nanomaterial. It's called cellulose nanofiber with a diameter of a few nanometers. Right? So they can be the strongest fiber ever. They're even comparable, even stronger than carbon fiber. Right? Of course, they have problems because they are shorter and they are at the nanoscale. But my research on wood is really about how to unlock the potential of this amazing, most abundant nanomaterials. So of course, there's another benefit compared to man-made materials. If you do the math here, actually 1 kilogram of biomass, or particularly wood here, can store actually more than 1 kilogram of CO2. Right? So if you can use wood for a long time, you can actually have a lot of CO2 benefit. Right? So you can lock the CO2 in wood, in buildings, in cars. So that will actually address a lot of climate change issues. Then, like many other materials, there are usually two approaches in dealing with wood. One is called bottom up, one is called top down. So bottom up approach basically is about getting the nanofibers from wood using chemical or mechanical process. Typically, you basically swell the fibers and you beat them mechanically, and you can extrapolate, taking the nanofibers out, and then you build them up. For example, you can make membrane, you can make transparent paper, and so on. And the other research direction is about top down. Like basically, you take entire wood, you do things inside the pore of wood, and make wood dramatically different. So this is a kind of the innovation in my group, actually, came in, about 10 years ago now. And I'm going to give you one example. So the motivation, of course, is to maximize the performance. We have to go beyond it just being green. Not many people will buy your material or product it's just because it's green. You have to show performance, much better performance. And the other goal is really to use more wood, from forestry, so you can maximize the CO2 benefit. So with that, a focus using the nanofiber to enable future technologies. Now, we can pretty much repeat everything people have done using other nanomaterials. And then, of course, we get a lot of amazing, interesting part. For example, transparent wood, insulation wood that can be a very good thermal insulator, and superwood I'm going to talk about. You can even mold wood. You can deal with ion transport. You can even make a wood like a bouncing, even like a ping pong ball, right? So they are all 100% wood, but if you process them in a different way, you dry them differently, you can get very different properties. So one of the focus is really to maximize the CO2 benefit is in buildings, right? So now if you look at building, steel is widely used. Of course, we all complain steel due to their intensive CO2 emission, but steel is still widely used, right? Especially in buildings here, right? What if we can replace steel using densified wood, right? What if wood can be as strong as steel? As I mentioned in the beginning, the nanofiber, um, from trees can be up to 7 gigaparsec. So they can be much stronger than steel actually. So this is actually the foundation and for our research. Right? So in this case, we basically take a piece of wood and we densify it. So we compare to any other densification method. In our densification method, we introduce a chemical treatment that allows us to soft wood, and that allows us to basically maximize the packing and densification of a piece of wood. And as a result, we can get to 600 megapar. Now we can actually get to 1.2 gigapar tensile strength. So think about actually in your vehicle, most of the steel actually with a strength about 400 to 600 megapar, right? So in this sense, Superwood is even comparable, even better than steel in your vehicle applications. Yeah. So the process is very straightforward. We are not using very high pressure. The pressure to densify wood is only 5 megapar. So you are not using pressure to get the strength. You are basically driving away water molecules in wood. And as you remove the water molecules, the fibers are naturally contact each other and they shake hands and they maximize the interaction. Then you can start to get a performance that is getting closer to the individual fibers. That is the logic, right? Again, this is 100% wood. We're not adding extensive glue inside. We're using the glue of lignin that is already inside the wood everywhere and to basically glue the fibers together, right? And we claim our wood is the strongest wood, and that is the major difference compared to any other densified wood in our market. So we call this one as a superwood because of the strength, because of the ductility, and this process is applicable to any kind of wood. It's fire and termite resistant, and it's actually very gorgeous. Actually, it looks very beautiful. It's very smooth. It's even shiny due to the density. And now, question is always about what kind of wood starting material do you need? And actually, this process of the densification basically remove the differences among different trees. The trees are different very often because they have different density due to the growth environment or the wood species. But after you densify it, after you push them to the maximum density, they become almost the same material, the densest wood, right? So this actually means that process can be applicable to many other locations. Of course, the details can be different. The process still need to be optimized, but the process can be applicable. So right now, we're funded by DARPA on using waste wood to make densified wood. Yeah. So that can make superwood even cheaper. Yeah. So I talked about mechanical properties. That's an intrinsic material property. On top of that, you can also make them into different shapes. Shapes are really important when you talk about structures, when you talk about material functionalities. Typically, you cannot mold wood. You cannot bend wood as you would uh, um, do for steel and for plastic. But in this case, we play with the water content. We can really fold and mold wood just like you done with plastics. So Yale is a very unique place to perform engineering research. I am in the School of Engineering, but Yale has a very strong school of architecture, especially for buildings, and they can basically use wood, for example, Superwood, design new building architectures, right? And there's also school of forestry. Yale is very strong in that. And then that basically take care of the raw materials. So I think Yale can have a very good ecosystem. I just had a wood actually conference in the summer, and we're having people gather together at Yale to basically talk about the engineering research. We're going to do it every other year. So I'm always interested in how to do manufacturing. This is actually funding from DOE ARPA-E. After the initial like $4 million funding, we received a 20 million scale up grant. And with that grant and together with investors' money, we actually have this plant actually at Maryland. Now it's fully functional. And this is also the headquarters of Invenwood. So now you can actually go to Invenwood website to reserve your samples, or your materials. And this actually was a ARPA-E event. We actually made, this is actually the small beam. Now we can make Superwood with a length up to 16 feet long. So the second topic is about wood batteries. So in this case, we are interested in addressing one of the key challenge in all batteries, that is about ion transport. We want to produce a highway, for ion transport, just like carbon nanotubes can be a highway for electrons, but there's no such highway actually for ion transport material. So if you think about battery operation, the simplified understanding is that when you charge the battery, the ion and the electron separate and they transport all the way to the other side and they meet. When you discharge it, you reverse the whole process and the electron goes back, ion goes back. Electron is much faster than ions. Ion transport is the problem, right? So how can we provide ion transport highways? It's very important. These highways should be very thin, very long, so that you can have a very low percolation threshold. That means you only need a few fibers to get the ion distributed quickly inside the battery. Right? So we know that the wood has these amazing fibers, right? They are very small and they are very flexible, so they can be incorporated into battery materials, but they don't conduct ions by themselves. And of course, even though trees pump ions every day for the growth, even nutrition, so they can be people actually use these fibers for batteries, but nobody can make the ion make the fibers ion conductive by themselves. So this is our innovation. We take the wood fiber, and they are made of small molecular chains, and then we basically open them up by soaking the fiber in the copper solution. Now, once you open it up, you can put the lithium ion inside the the molecular chains. So you have a lot of ions. That is the high N number. And the distance between the molecular chains is not that big. So the ion can transport very quickly between the molecular chains. That means a very high mobility. The number N times mu give you very high ion conductivity. So we actually get almost the record high ion conductivity in a dry wood fiber. Now you can use this fiber into almost any kind of batteries, right? So this actually was an ARPA-E project. We just finished this project. We meet all the milestones, and in this particular case, we're using NMC with lithium metal, right, for high energy density batteries. Yeah. So this is the process, how it looks like. You take the fibers, you almost use the kimchi process. You soak it for about 3 weeks, and the copper ion get into the molecular chains, and then you put the lithium ion into the molecular chains. Now you can transport ions. So these are the kind of the fiber transport. We get a conductivity up to 1.5 millisieverts per centimeter at room temperature. right? Of course, it's going to be even higher at a higher temperature. So it's basically like a freeway systems, and because they're very very long, you only need a little bit of them to conduct ions. So the plot on the right side shows you the activation energy is very low, means this fiber actually have very good performance at low temperature, right? So you don't have this typical glass transition temperature of polymer electrolyte. Right, so now you can use this fiber to make a membrane, make a nano paper that is very strong and also ion conductive. You can also make these fibers into battery cathode to basically enhance the ion transport to improve or increase the fast charge performance. So I always tell my student that is almost like a soy sauce, right? You can add a little bit and you can make your battery much better. Right? So this is actually what we've done. This data out of the APAI project. So we demonstrate a 400 watt hour per kilogram battery, and we can maintain 80% of capacity even at a 1C. And to the right side, that is quite a surprising to us that with this solid state. Okay, this is not a gel or liquid. This is a solid state fiber. We actually had amazing safety performance. The number here to the right actually basically tells you how much heat is actually released. You can see that ours is actually much lower even than LZO, that is the oxide battery, right? So with that, we're working with USDA and we're working with the paper industry, paper companies about how we can basically manufacture these fibers. And then we are interested in working with the battery companies to incorporate these fibers in their battery chemistries, right? So we are more than happy to work with and battery companies that it's interesting using these fibers. Okay, so the third story is about catalyst. So in this case, I'm going to show you how we can use a very unique shock process. Means everything happened very fast. You heat it up, you melt everything, you quench it down right away. You can lock a lot of compositions that is not possible in the traditional catalyst discoveries. And then very often we're trying to address the critical materials because a lot of catalysts, the good catalysts, for example, platinum, they are very expensive and they basically considered as a critical material, right? So catalyst is a huge market, and many biotech, chemical plants, and the drug discovery, manufacturing, they all need a catalyst, right? So catalyst, especially heterogeneous catalyst, is a huge market, right? And typically people make catalyst using this process. They heat it and then they follow the phase diagram and then they finish and they take it out, right? So you basically follow the typical phase diagram. You know that, for example, gold and nickel, you say, I cannot make it. No, don't do that. But a lot of catalysts requires you mix some elements that they usually don't mix. For example, cobalt moly for ammonium chemistry. But in that case, we have to find a way to mix them, right? So that means we have to break the rule. We cannot follow the thermodynamics. So in this case, we basically increase the temperature to very high temperature. In the phase diagram, at high temperature, the phase diagram is very simple. Everything mixed. And you just quench it very quickly as fast as you can. Then you can maintain the mixing that you have at the high temperature, right? So you can maintain the mixing that usually they will separate. So that is show you, look at the right side. You see that usually conventional method, they will separate, they will be immiscible. But if you use the shock method, no matter what, okay, we can mix them in a homogeneous structure. So this homogeneous structure means these two atoms can talk to each other. So you can design on the two different properties of two atoms. Now you can basically realize the catalyst design. For example, silver and the copper here, if you look at the phase diagram in the bottom, it's white, means they don't mix, they don't like each other. And actually, when you make this catalyst using traditional method, they don't like each other. But if you use the shock method, you can see they're homogeneously mixed. They're basically trapped in these nanoparticle structures. Now, with that, you can even further design catalyst, something called a high-entropy catalyst. So one of the major problem, a challenge for catalyst, in addition to using low-cost element, is about the stability, right? And one of the key concept in here is about high entropy. Basically means if you have a random system, if you have a disordered system, like the bedroom, to the right side, it's very stable, right? If you don't put energy to organize them, this randomness is going to be here for a very long time. And so the idea here is that how can we use this concept using high entropy, having a lot of elements, and you randomly mix them into a particle, and thermodynamically, you can use a high entropy concept to stabilize the catalyst. And now you not only get low cost catalyst, but also they can perform with very good stability. So this is the idea, how to do it, right? So basically, we have the salt. You can also have the elementary powder. You mix them, and then you just heat it up, okay, to very high temperature, and you quench it down right away. So typical process is less than 1 second. So that also means you can continuously manufacture it by flowing method, by dropping the particle through the heater, right? So you can see here left and the right, right? It's only 55 milliseconds at 2000 degrees C, you can make these beautiful nanoparticles. So this is the process. So usually we need just one shock, okay? I just keep showing this so that you get an idea, but in our experiment, we just need one shock, right? What happened in this one shock? After the shock, you see all these homogeneous nanoparticles. And if you zoom in to see on the bottom right, you have this diffraction pattern, right? So you see these elements not only uniformly mixed, but also form a crystalline structure. So they form this FCC structure. And at the same time, the lattice distribution side, they are all random. Yeah. So we can mix platinum, copper, for example, they usually don't mix. Now, in this case, they will mix. So now, without any constraint, you can start to design your catalyst. You can just keep adding elements, and you can make it using this shock method. So this is really important for now. It's called AI for catalytic discovery. And you don't only have a lot of constraints when you design elements. And with rapid screening of the catalytic performance, we can actually do this, basically quickly discover what is the optimal composition. Yeah. So this is a real another example case that funded by DOE again. And in this case, we're trying to design cobalt and ammonia catalyst. In the cobalt and ammonia on the two sides of this volcano plot, right? So one is binding too strong, the other binding is too weak. If you have both of them, you will have to optimize the binding to basically maximize the performance. But if you look at the plot in the middle, you see that they don't mix at all. Right? So in this case, we mix them using high entropy, using the thermal shock, and we show excellent performance here. Right? So we also done some other catalytic reactions using ammonia oxidation, and we actually showing performance stable up to 1,000 hours. That is, I think, is good enough for industry applications. And you can tailor the heating protocol. You can make a morphostructure, you can make phase separated, you can make intermetallic. You play with this TTT diagram. Yeah. So just like a shelf in the kitchen, you basically control the time and temperature, and you can get all kinds of compositions. I demonstrate alloy metal. You can also do oxide, sulfide, carbide, and even morph structure. So it's a platform. Once we identify one particular catalyst, we can use the same process, same patented technology to basically manufacture other catalysts for a whole broad range of catalytic applications. In this case, we're making 1 kilogram per hour catalyst for ammonia oxidation applications. Okay, let me give you the fourth example. In this case, I will show you something called ultra-fast high-temperature sintering. So what does that mean is that usually if you sinter a piece of glass or sintering a battery ceramic materials, typically it takes about 10 to 20 hours to have the good density, to have a good uniformity for the membranes. But if solid-state battery is going to work, if solid-state oxide fields are going to work, manufacturing is going to be one of the key challenges. At the same time, I'm also going to show you that we actually using this rapid sintering, we can actually get an even better performance in addition to faster speed. Now, why is that? Basically, in our process, we're going to melt everything and we're going to freeze them. We're going to densify it right away altogether. in a few seconds. So in this case, we're not dealing with biomaterial like wood. We're not dealing with, it's low temperature materials. We're dealing with high temperature materials. For example, high temperature jet engine, solid state battery materials using ceramic membranes, solid state oxide fuel cells that are using oxide membrane as well. So all these things, they have these challenges for next generation of new materials. They have to discover what's the new material. And once they discover it, they have to manufacture the material, right? So here is usually the typical process. People take the powder and put in the furnace, heat it for 5 to 10 hours, and they have to break it again and then press into a pellet. And to heat it again, in this step, is called sintering. You're trying to make a dense membrane from the right composition. So it takes like 20 hours, starting with the powder. The lithium loss is everywhere into your chamber. You contaminate your chamber, and now so that you don't have a good performance because you're using lithium metal, it takes 20 hours, so you don't get the manufacturing speed. Right. So in our process, we use this high temperature. Instead of having the furnace heated up, we put the material right on top of the furnace. So this is the furnace, how it looks like. This is the heater. It goes to 2000 degrees C, for example, or 3000 degrees C. Usually we use 2000 degrees C. And you put the material right on top of it. And just like a pizza oven, you have one on top, one on the bottom. And in a few seconds, you can actually finish the sintering. Yeah. So this is actually how the process looks like. Not two steps, just one step, right? You have the pellet, you push it in, and you push it out. Okay, the whole thing only takes a few seconds. And actually, the principle in my lab is that everything has to happen less than 10 seconds. And in that way, you don't get contamination. You don't have lithium loss. The lithium doesn't have time to evaporate. So you basically lock them in the structure, and we don't use pressure. And I hate using pressures because if you're using pressure, it's going to be very hard to change samples. So that means it's not going to be good for manufacturing. No pressure means you can change samples very quickly for manufacturing. So with this platform, with a heater on top, with heater on the bottom, you sample in between, or sometimes just the heater on top, no heater on the bottom. You should just scan the heater over your coating or sample. You can make ceramic materials, you can make glass structures, you can make refractory metals for jet engines. So these are some quick examples just to show you that we not only get the speed, but also get the performance. You see the density that you can barely see any holes because you basically melt it. And we also demonstrate amazing battery performance for solid state without lithium dendrite formation. Yeah. So I think this is really unique for basically discovering materials that is basically a bottleneck, especially for metals and ceramics. Now, think about that. You can make a lot of ceramics in a furnace, and typically our furnace can be used for about 40 times and until we basically trash them. Yeah. And they are very, very low cost. Right? So you don't need to worry about contamination as well. Yeah. Right. And I don't have slides for manufacturing, but we do have a project funded by DOE for the battery membrane manufacturing. We're making like 4-inch by 4-inch or 6-inch by 6-inch membranes using this method. Again, we are getting not only the quantity, but also getting the speed. Yeah. So let me show you I think now is number 5 technology is the artificial sun. So in this case, we are pushing the temperature to even a higher value, higher than the surface of the sun. The surface of the sun is about 6,000 degrees C. Okay, here I'm talking about 8,000 degrees C. So why do we need that, right? Using this extreme temperature, 8,000 degrees C, you can pretty much break any bond in any materials, like metals, forever chemicals, and nitrogen gas, carbon, all these bonds are very weak in this temperature. And one of the technology we're trying to do is basically for space, so for space application for fusion energy as well as for graphite. That is a critical material here as well. So what is the principle? What is new? So I think everybody see the lighting, right? Lighting is not a constant, stable, behavior. It comes, it goes, right? It's a linear behavior, and it's very high temperature, but it's not stable, right? So if you're using almost like arc discharge, right? You can use that to make materials, but it's not stable. So that means it's really hard to get the stable yield. You don't get, and very often you have to cook it again if you're trying to make the material. So as a result, you're wasting energy. To the right bottom, people also know how to make stable plasma, but for example, PCVD, plasma enhanced CVD, those plasma is very stable, but temperature is really low, right? Couple hundred degrees C. But here we're talking about the combination with the two, right? So how do we do it? And so the way to do it is that through this tip enhanced plasma. So we invented this about 2.5 years ago. We had a paper in Nature. What's happening here is that so instead of using two metal plate, we have tips, like carbon tips, and you know where you're going to shoot an electron, you know where you're going to collect the electron. So it's very stable, relatively speaking. And then you have a lot of plasma tips. You have like, for example, 10,000 tips, right? And all these tips will generate plasma, and all these plasmas will basically support each other. And as a result, you can have a very stable plasma. And it's striking here that the voltage of achieving the 8,000 degrees C plasma is only about 30 volts. So the voltage is really, really small compared to otherwise you using metal plate, you would like thousands of volts to achieve that kind of plasma. So that means you can turn this plasma on and off, and you don't have to have a special machines, and you can achieve this plasma in almost like a portable systems, right? So, and I think this is really important for not only for material discovery, but also for manufacturing, especially if you have a distributed systems. And so this actually we won this R&D 100 this year, and this is the Nature paper. If you're interested, and Nature actually put a YouTube video together. If you're interested in see more of the details, you just go to YouTube, search super hot plasma, okay, and you will see the video about our work here. So this is actually how the plasma looks like, right? And if you visit my lab, usually I show people this process, and you can see the plasma is on and off very easily using a small voltage. And here again, we're talking about 8,000 degrees C, right? And we can melt pretty much anything. And now we're trying to scale up the plasma system at Yale University. And the plasma can also be on for a long time, for about 20 minutes. And here I try to show you up and down so that you get an idea of tunability of this plasma. So we here are using plasma, and we're very busy to make new materials. So this is one of the project, launched by APAI a few months ago. And here we're basically convert biomass plastics, for example, into battery graphite through the fly process. You basically have plasma, you just fry these chips or drop this through the plasma, and sometimes the time is like few seconds, and we can actually get this thing done, yeah, right? And of course, high temperature materials, refractory metals. Here we demonstrate hafnium carbon nitride as the highest melting temperature material with a melting temperature more than 4,000 Kelvin. And then we successfully make a pellet out of hafnium carbon and hafnium nitride, and you mix the powders together and you sinter them, and in a few seconds you can get this hafnium carbon nitride. And why it's important? What's the big deal, right? And this is one of the potential applications for the shielding, heat shielding materials. And then we're also interested in making metallic glass. We're working with Professor Yan Shuo here, who is the expert on metallic glass. And we're using this again as a new platform to quickly make super hard materials like refractory metals, for example, and we completely melt them, and we completely resemble them back into a new material. Yeah. You basically think about you break all these atoms up and you put them back again. Okay, so it's basically remake materials from an atom up. Okay, let me give you the last example. I hope my time is okay. So in this case, I'm going to show you how we can use the pulse heating. It's almost like a music. Okay, you basically have different node, and you heat it and you stop it. Heat it, you stop it, right? And there's a motivation of doing that. And you can couple together with different kind of reactors or heaters. For example, you can 3D print a reactor so that you can have plastics flow into the pore structure, and as they flow, they getting heated up, and you are using the heating to break the bond and to reform the materials. In this case, we don't use any catalyst. Catalyst usually is a problem for stability, and the catalyst usually is a problem for cost. So here, I think our reactors will basically have a better stability. So this is actually what industry is doing right now, yeah, right. So you see this giant, chemical plant, and they are using basically conventional fuel, and you heat it up, you turn it on, it's going to be always on. And it's hard to control the kinetics. You say, oops, I changed my mind, I want to stop it, or I want to have this kind of controllability of reaction. For example, in front of you, you have this methane pyrolysis, right? You have one carbon, you have another carbon, you cannot stop it. So in the end of the day, you get carbon black, right? And you get hydrogen. Very often people are interested in hydrogen, and you're trying to deal with carbon black, right? So, but of course, the methane pyrolysis, you can do a lot of interesting product. For example, you have a C2 product, which is much more valuable, but you cannot do that because the time scale adding one carbon is very, very short, right? It's only like tens of milliseconds. You have to stop it. Otherwise, they can just keep adding carbon, right? So in this case, our idea is that using this, again, using the electrified heating, think about your light bulb at home, you turn it on, it's on right away, you turn it off. Now, if you can just turn on and off by applying a current, now the current will be translated into a heat. That is your heater. And now you flow with the current, like chemicals, right? So this is the another way of doing heating. Now, in this case, you flying or you flowing chemicals or gas through the porous heater that is basically heating upside down, up and down to basically control the cutting, purging the chemicals, right? So I think this is the a basic concept. So carbon is very important as a heater because carbon is very light and carbon has a very fast response, right? So in this case, we show you this C2 product and we compare to literature. And remember here, we're not using any catalyst, right? And the reason you need a catalyst because you don't have enough energy to do the reaction. But if you have enough temperature, we heat it up, then we can break the bond, we can do the reaction, and then we quench it down so that we can get the product out and we do it again, right? So to highlight, there's no catalyst used. And my postdoc now, who is a professor at Purdue University, has done a lot of work. He's continuing work on this platform, and he generated a lot of different kind of chemicals, including liquid product, including gas product. And very recently, we have a paper in Nature Chemical Engineering. I think this is really interesting in terms of the heater design. And in this case, we carefully tune the porosity using 3D printing. And we also realize this heater using other traditional low-cost fibers. Yeah, but in this proof of concept, we have this tunable pores. So you start with big plastics. Okay, they are very giant. You heat it up, they move very slowly, and once they become a small molecules, they can flow faster, and you can exhaust it basically from the top, right? So if the plastic is not being converted yet, they're still very big. They will stay there until we heat it again, until they become small molecules and they flow up, right? So this is actually how the process looks like, and we have this kind of setup in the lab. And the idea here is in the future you can have these distributed systems, and you can have a lot of this kind of small reactor, and they can individually be heated up and down, and they just pour the C8 to C18, those carbon product as a jet fuel, yeah, right? So in the end of the day, who cares? I think we have to be low cost. We have to have a better selectivity, and we also have to basically from cost point of view, right? So this actually done through collaboration with Professor Lima at the West Virginia. It's expert in this kind of chemical plant modeling, and we have this kind of data showing that we pretty good in terms of cost, yeah, in terms of performance as well, yeah. So I think with that, I would like to conclude, and mainly funded by DOE, different agencies, and also DARPA has this wood project, NSF, and a lot of collaborators. You can imagine. I'm also collaborating with Professor Jay Hong here as well, and hopefully we'll have time to talk about that kind of collaborations. So I'm very open for collaborations. I think together, I think we can do a lot of interesting research, and through industry, through investors funding, hopefully we can make an impact to change the world, so to speak, to some extent. And I'm more than happy to answer any questions you may have. And apologize for rushing through so many slides. And I just want to make sure that I have time to cover all the materials. And now we actually have time to answer questions. Yeah, thank you so much.
Thank you so much, Bing. I'll be happy to open the Zoom for the questions. Any questions?
Yes, I have a question.
Yes.
Dr. Hood, yeah, thank you for the presentation. My question is actually regarding the densified wood for buildings.
Yes.
I'm wondering how resistant is this densified wood to biological degradation? So like fungi and termites.
Yeah, that's a very good question, right? So, the uh, uh, for degradation is a combination of UV, water, and exposure, for a long time. This densified wood is going to be it's going to be a problem for fungi or those, because they don't have the pore to attack, right? So they can only scratch from the surface, right? And I mean, in the end of the day, it's still a piece of wood. Okay, I think if you don't do any coating at all, so it is 100% of wood if you don't do any surface coating, right? But for some applications, if the wood need to be outside the building, it's for an environment that has a lot of access to UV, water, and the bio species. In that case, the coating will be necessary.
Got it. Thank
Yeah.
you.
Yeah.
Any questions from folks in Korea? You are welcome to ask questions in Korean language. I'll be happy to translate.
거기 뭐 기획처는 뭐 내가 파일 해니까 해버리면 되지 뭐냐고 그래서 나는 잘 모르겠다 그렇게 하는 거
I'm not sure if that's a question. Maybe that's a conversation. Well, if you don't have an immediate question, that's fine. I just left contact information for Dr. Hu in the chat box. And I also uploaded the link for hot plasma video that Professor Hu just mentioned. So thank you so much again for your attendance. Down the road, please do not hesitate to contact me in the email that you have in the chat box. And I'll be happy to be a mediator to connect you to Professor Hu. As I mentioned before, Professor Hu's research spans across the field, all the way from battery to aerospace engineering, and as well as any structural materials that you can imagine, including catalyst, falsified wood. I hope you have a chance to visit Yale at some point. I had a privilege to watch that artificial sun that Professor Hu has created. It was just really phenomenal to see that. By the way, our next presentation is going to be on Tuesday, October 21st by Professor Brian Scaselati, and he's going to talk about robots that serve special population in the home, especially elderly people. So having more population in the elderly people is a new phenomena that we are dealing with in Korea, and we have a tremendous opportunity in that sector in terms of business and commercial growth. And I'm sure the next presentation will be of tremendous interest to many people in Korea. All right. Thank you so much again for Dr. Hu for a wonderful presentation. And thank you so much all for the participation. Look forward to seeing you at the next seminar.
Thank you for having me here.
Okay, bye-bye.
Bye.